Okay, in this video, we'll be talking about the potential divider, potentiometer, and also Wheatstone bridge. Recall that in the video 15.2, which is Kirchhoff's law, I told you that this is the formula for the potential divider, and then this is the formula for the current divider. Okay, so remember this. When R1 and R2 are connected in series, you can straight away find the potential difference across R1 is R1 over R1 plus R2 times E. Okay? And then a potential divider is used to produce a fraction of the voltage supplied by a source of current. That means that right now your source is this one. This is your source. Okay, and then you want to find a fraction of the voltage of the source. And therefore, a potential divider is used to produce a fraction of the voltage supplied by the source. Okay, so state the function and the operation of a potential divider in an electric circuit. The function is to obtain a fraction of the voltage supplied by a given source to the circuit. Okay, and then the operation is like this, okay, which is the formula of the potential divider. A rheostat may be used as a potential divider. A rheostat is just a variable resistor. That means that you can control the resistance of the resistor. Okay, therefore we call it a variable resistor, which is a rheostat. Which circuit shows a rheostat is being used to provide a fraction of voltage of power supply to an external circuit? Okay, so this is an external circuit. And then this is the circuit of the driver cell. And then the circuit of the driver cell should be a complete circuit. Okay? And then the external circuit can only take out a fraction of the potential of the driver cell. Okay? A 6-volt cell with negligible internal resistance, a potential divider X with a slider P, two switches S1 and S2, and two identical bulbs B1 and B2 are connected. P is at the center of the potential divider. The resistance of X is 100 ohm. Bulb B1 and B2 are each rated as 3 volt and 9 watt. Please calculate the resistance of the bulb when it functions normally. Okay, so for the bulb, you know that P is 9 watt and then V is 3 volt. So by using P equal to V squared over R, you can get the resistance of the bulb. When both switches are closed, what happens to the bulbs? Okay, when they are both closed, you realize that actually the resistance here is same as the resistance here. Okay, so the potential difference across here is 6 volt. So that the potential difference across here is 3 volt. The potential difference across here is also 3 volt. The potential difference across here is also 3 volt. The potential difference across here is also 3 volt. And then there's actually no current flowing through the slide wire. Okay, there's no current flowing through this slide wire here. Okay, so you know that the potential difference across bulb B1 is 3 volt, and then the potential difference across the bulb B2 is also 3 volt. So you know that the bulb can light up normally, okay, because the bulb are rated as 3 volt. And then this is the potential difference across it. So you know that the bulbs can light up normally. Now switch S2 is then open. What happens to bulb B1? Please explain your answer. Okay, now S2 is open and then S1 is closed. So you know that there's no current flowing through here. Okay, so you can delete this part of the circuit. Okay. So when S1 is closed and then S2 is open, your circuit is like this. Just now, when both switches are closed, that is when both of them are closed, your circuit is like this. And then just now I told you that there's no current flowing through here, okay? Because the potential here is same as the potential here, so of course there's no current flowing through the slide wire, okay? So just now, actually you can simplify the diagram because you know that the 50 ohm resistor is connected in series with the 50 ohm resistor, and then the 1 ohm resistor is connected in series with the 1 ohm resistor. Okay, so by finding the equivalent resistance of the whole circuit, you can find the current flowing out of the battery, which is this I. Okay, I is this. And then by using the formula for the current divider, you can get the current that flows through the bulbs. The current that flows through the bulb is 3 ampere when both switches are closed. Okay, just now, you know from the question that both bulbs are rated as this one. Okay, so you know that the normal current is 3 ampere, and then this is exactly the current that flows through the bulbs when both switches are closed. So you know that just now your answer is the bulbs can light up normally, okay, because the current matches with the normal current. Now, S1 is closed and S2 is open. Therefore, your circuit becomes this one. And then you find the equivalent resistance of the whole circuit. Okay, that is, you know that the equivalent resistance here is 0.98 ohm. And then the total resistance is the whole circuit is 0.98 ohm plus 50 ohm, which is equal to 50.98 ohm. And then you want to find the current that flows through the whole circuit, okay, by using V equal to IR. And then you know that the current that flows from the battery, which is IT. T means total, okay, the total current that flows out of the battery. And then now, by using the equation of the current divider, you find the current that can flow through the bulb B1. And then now you realize that the current that flows through the bulb B1 is now 0.115 ampere. Just now your current is 3 ampere. So you realize that the current really drops to a very, very low value. When the current is too small and much less than the normal current, then the bulb will not light up. Okay? So I think the tactic to solve this problem is that you really try your best to find the current that can flow through the bulb B1 when the S2 is open and also when S2 is closed, so that you really can know the numerical value of the current that flows through the bulb B1 in both cases. Okay? The rheostat is adjusted until the reading of the ammeter becomes 0. If R is 4 ohm, please find the value of E1. Okay, straight away you use the formula of the potential divider, then you can get the value of E1. Okay, E1 is just a fraction of E2. Okay, a potentiometer consisting of a uniform slide wire PQ of length 100 cm is connected to a power supply of 2 volt. The internal resistance of the driver cell is negligible. That means that for this driver cell, it does not have any internal resistance. When the switch S is open, the balance length L is 80 cm. And when the switch is closed, the balance length is 50 cm. Find values of E and R. Okay? So you know this is the switch S here. So when switch is open, you know that it is measuring the EMF of the cell. So when the switch is open, the balance length is 80. Okay? So 80 divided by 100 times 2 is equal to 1.6 volt. So you know that 1.6 volt is the EMF of the cell. When switch is closed, that means that this circuit is now a complete circuit. So you are now measuring the potential difference across the battery and also the potential difference across the resistor. Okay, so now the balance length is 50 cm. Okay, so you know that 1 volt is the potential difference across the battery. And then by using E equal to V plus IR, you want to find the internal resistance. But before this, you should find out the current that flows through this circuit first. Okay, you know that the potential difference across here when the switch S is closed is same as the potential difference across here, which is also same as the potential difference across here. Okay, so by using V equal to IR, you are able to find the current that flows inside the circuit, and then you substitute I inside here, you can get the value of the internal resistance. Okay, actually, do you know why the potential difference is directly proportional to length? Because V equal to IR and then R equal to rho L over A. By using this equation, you know that V is directly proportional to L. Okay, so the larger the balance length, the larger the potential difference across that length. Okay, and then when the galvanometer shows 0 reading, then is the balance length. That is when the potential difference across here is same as the potential difference across the balance length. In the potentiometer PQ is a slide wire of length 100 cm and resistance 6 ohm. The 1 volt and 12 volt batteries have internal resistances of 1 ohm and 2 ohm respectively. Find the balance length L. Okay, so you know that this circuit is complete, and therefore you are now measuring the potential difference across here. Okay, you know that the potential difference across here is the same as the potential difference across here, which is also same as the potential difference across here. Okay, E equal to V plus IR, and then you can get the current flowing inside this circuit. And then by using V equal to IR, you know the potential difference across the resistor is 0.5 volt. So you know that the potential difference across the balance length is also 0.5 volt. And then by using this, you are able to find the balance length, because you know that the potential difference across PQ is just 9 volt. Okay, so 9 volt corresponding to this length. 0.5 volt corresponds to this length. Okay, just now you already learned that V is directly proportional to L. Okay, a potentiometer consists of a battery of EMF E with an internal resistance R, a resistor of resistance R, and a slide wire XY. The length of the slide wire is L and has a resistance R. If the balance length is L over 4, please find the EMF of the cell. Okay, please find the EMF of this cell. You know that the potential difference across the cell is now the EMF of the cell, which is equal to 0.25 L times R over L, because the resistance of the whole wire is capital R. And then now you are only taking a quarter of the slide wire SY. Therefore, your resistance is now 0.25 R only, and then divided by the total resistance inside the driver circuit, which is R plus small r plus another small r. Okay, times E. Therefore, you get this expression. A potentiometer is used to determine the internal resistance and the EMF of a dry cell E2. The EMF of the driver cell is 2 volt with negligible internal resistance. The variable resistor R1 is set at 1 ohm. The slide wire XY is 100 cm long and has a resistance of 3 ohm. The resistor R2 has a resistance of 5 ohm. When switch S is open, the balance length XZ is 90 cm, and when switch S is closed, the balance length changes to 80 cm. Determine the potential difference across the slide wire XY. Okay, you know that the resistance of the slide wire XY is 3 ohm, and then the total resistance in the driver circuit is 3 plus 1 ohm. Okay, so by using the formula of the potential divider, then you can find the potential difference across SY. Please determine the EMF of the cell E2. When switch S is open, this length, that means that the potential difference across here corresponds to the EMF of the battery or the cell, okay? And then when the switch S is closed, the balance length here corresponds to the potential difference across the battery or the potential difference across the resistor. Okay, so when you want to find the EMF, you have to look for the balance length when the S is open. Okay, so by using V is directly proportional to L relationship, you are able to find the EMF of the cell. Okay, you remember why V is directly proportional to L here? Because V equal to IR and then R is equal to rho L over A. So you know that V is directly proportional to L. Okay, so V is directly proportional to L when I and rho and also the area are all constant. Okay, so determine the internal resistance R of the cell E2. When switch S is closed, the 80 cm corresponds to 1.2 volt, which is the potential difference across here, which is same as the potential difference across here, which is same as the potential difference across here. Okay, and then by using V equal to IR, you know the current flowing through this circuit. And then by using this formula, you are able to find the internal resistance. Okay, now in the Wheatstone bridge, normally you have 3 known resistors and then you have 1 unknown resistor. And then by finding the balance point, that is the reading of the galvanometer is 0, you are able to find the resistance of the unknown resistor. So this is the Wheatstone bridge. And then you remember that inside the Wheatstone bridge, when G has no reading, that means that when the reading of the galvanometer is 0, the current will flow from here to here. And then the current will flow from here to here. There's no current flowing through the galvanometer itself. Okay, so by using this, you know that the potential difference across here divided by the potential difference across here is equal to the potential difference across here divided by the potential difference across here. Okay, and then the current flow through here is called I1. The current that flows through here is I2. And then the current flow in the whole circuit is called I. Okay, and then you know that I equal to I1 plus I2. Okay, from the Kirchhoff first law. So you need to remember that when it comes to Wheatstone bridge, R1 over R2 is same as R3 over R4. Or you can say that R1 over R3 is equal to R2 over R4. Both are correct. Okay, so by using this formula and then you substitute everything inside, you can get a value for X. Okay, you either use R1 over R2 equal to R3 over R4, or R1 over R3 is equal to R2 over R4. Which galvanometer in the circuits below shows 0 deflection? Okay, first of all, you look at these two diagrams. You know that the potential here is definitely greater than the potential here. Okay, because the current flows like this. So you know that the potential here is definitely greater than the potential here. And then here is the same. That is, Vx is much greater than Vy. Okay? Therefore, you know that the galvanometer in both cases cannot show zero deflections, so they are wrong. Okay. For this one, the ratio 3/4 is same as the ratio of 6/8. So this is the one that will give you zero deflection. For this one, 3/8 is not equal to 6/4. So definitely you cannot get the zero deflection from this galvanometer. And then remember, when the galvanometer shows zero deflection, that means that the Vx and Vy are the same. Okay? That means that the potential difference across the galvanometer is 0. Okay? So remember, V equal to IR, the V refers to the potential difference. That means that V is the Vx minus Vy. Okay? So when Vx is equal to Vy, the V, which is the potential difference, is equal to 0. So that there's no current I equal to 0 in the galvanometer. Okay? The bridge will be in equilibrium. That means the Wheatstone bridge will have a 0 reading on the galvanometer if X has a resistance of, okay, you know that 15 divided by 10 is equal to this equivalent resistance divided by 24. And then this equivalent resistance is 36 ohm. So 1 over 36 is equal to 1 over 72 plus 1 over X, because you know that X and 72 ohm resistors are connected in parallel. Okay, so ultimately you can know the value of the unknown resistance X. Okay, so that's all in the chapter 15. Hopefully you can learn something from this. Thank you.